So I first want to mention a couple of things that I should have said last time, which was in fact yesterday. One thing is that I should have mentioned explicitly that partial derivatives commute. The derivative first with respect to y and then with respect to x is the same as the derivative first with respect to x and then with respect to y. I'm sure you know that, but it's worth mentioning, I think. Also, partial f, partial x is a tedious thing to write and to code, and so often I will write it this way. And similarly, partial y of f is partial f, partial y, and so forth. So that's the first thing I wanted to mention that I should have mentioned yesterday. Another is that the signs in those equations, 266 and 7, that I thought were wrong are actually correct. So these signs are actually right. What happens is you have here an x gradient. When it comes inside, of course, it's still an x gradient. If you make it a y gradient, make it an r gradient, you get a minus sign. But then if you integrate by parts, you get another minus sign. So you still have a minus. Same thing here, an x gradient gives a minus sign when you turn it into an r gradient, but then when you integrate by parts, the minus sign goes away. So that was another thing to mention. There is, on the other hand, an erratum coming up, and I'll have to tell you about that when we get to it. Let me just remind you, though, of the Helmholtz decomposition, which is in the notes, but not in the second edition. And the statement is that basically any function, any suitably smooth three-dimensional vector field, a field, by the way, is a function of space-time, or a function of position, or more frequently a function of position in space. That's what we call a field. Anyway, any suitably small vector field function of three variables that's suitably smooth can be written as the gradient of something, of a scalar, that is to say a single function of x, and then a curl of three functions of x. And so that's something that's used in electrodynamics enormously, because what we do is we say, well, the magnetic field we say the magnetic field. So the start of class was there. The magnetic field, we say, has no divergence. And so here we can write the magnetic field simply as the curl of something. So the magnetic field is simply the curl of something else, which we call the vector potential. The electric field, on the other hand, we write as the gradient of something plus the curl of something. And we don't often do that, though. And so I'd have to pause and look at Maxwell's equations again to figure out exactly whether that's promising or not. Let me remind you one more time that covariant and contravariant vectors, which is a concept that is sloughed over almost completely. At least it was when I was a student. I hope things are better now. Anyway, covariant and contravariant vectors are, it's a term that's used differently in different areas of physics and mathematics. But the fundamental mathematical definition is that if you have if under a general coordinate transformation where, and by that one means here that x prime I is x prime I of x1, x2, dot, 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 xn. So this is what is meant by, actually, I now see that I switched from superscript to subscript without intending to. So let me see if I can go to my Jiffy eraser here and go back to here. And so 1, 2, n. The idea then is that the derivative with respect to x prime k, say, is the partial, well, k was a mistake, obviously. The derivative with respect to x prime I is the partial with respect to xk times the partial of xk with respect to x prime I. That's just the chain rule. And that's how derivatives transform. And any vector that transforms like a derivative is said to be a covariant vector. On the other hand, the coordinate differentials dx prime I is partial x prime I partial xk times dxk, and any vector that transforms this way is called a contravariant vector. Normally, we write covariant vectors with lower indices and contravariant vectors with raised indices, but one can always raise and lower indices. And the way you raise and lower indices in general relativity is that you say that VI, for example, is GIJ, VJ, and say VK is GKL, VL, where G here is the space-time metric. In special relativity, in general relativity, GIJ is a 4x4 matrix, or a 4-component, or 16 components, since there are 4 I's and 4 J's and so forth. When we go from special relativity, from general relativity to special relativity, this turns into eta ik, and eta is the matrix -1, 1, 1, 1, zeros everywhere else, so zeros here. So that's just an aside there. So now we'll go on to Fourier series, and the idea here is that these phases, e to the in x, for integer n, are orthonormal on an interval of length 2 pi. And when, of course, you divide by square root of 2 pi. And so the integrals are simply that this is e to the in minus mx over 2 pi. And when you do the integration, if n is not equal to m, then when you do the integration, you just get e to the 2 pi I n minus m minus e to the minus 1, and e to the 2 pi I times any integer is 1, and so you get 1 minus 1, which is 0. So just to make that perfectly clear, or maybe clearer, you get, when you integrate, you get e to the 2 pi n minus m minus e to the 0, which is 1, and you're dividing by 2 pi. And on the other hand, you're you're dividing by 2 pi, but in any case, it's 0 if n is not equal to m. But on the other hand, if n is equal to m, then this is an integral 0 to 2 pi e to the 0 over 2 pi dx, and that's just equal to 1. So that's where this fundamental relation comes from. And so then the orthonormality of these functions allows one to, or is what Fourier used to construct his Fourier series. And so what you do is you write f of x as some numbers times these orthonormal functions, and you sum over all possible n's. Fourier, as I understand it, was using, invented Fourier series in order to discuss how heat diffused in solids and liquids and I guess gases. So as usual, these great figures of the past were invented various tricks, which now we revere, and they invented those tricks to do things that were much more complicated than the tricks themselves. Anyway, this is said to be a Fourier series. When he invented it, my understanding is that a lot of people objected, thought he was being silly, and what he was doing wasn't meaningful, but obviously it was. I don't know why I capitalized that S. Let me see if I can uncapitalize it. No, I don't even know where it is. Well, all right, forget about it. Anyhow, so what you do is you write the function this way, and then you use the orthonormality to identify the coefficients. And in particular, if you integrate the function from 0 to 2 pi multiplied by e to the minus I nx over root 2 pi, and then apply this orthonormality relation, what you get is f sub n. And so this is our formula for f sub n. It's this integral. And then the Fourier series is the sum of these. One can interpret these in terms of Dirac notation, letting this phase be an inner product, interpreting as an inner product of a ket n with a vector x. And then the identity operator is an integral of these outer products, and or equivalently a sum of the outer products for integers. And the inner product of two of these is, when you insert the identity operator in this form, you see it turns into this integral, which repeats the orthonormality. Or if you use the orthonormality, you get delta nm or mn. You can also you can also recover the function f of x in Dirac's terms by saying it's the inner product of x with f. You insert the identity operator in this form. This gives us the numbers nf, and then these functions, and you get the Fourier series like that. You can also take the inner product of two arbitrary, an arbitrary bra, an arbitrary ket. You insert the identity, you get gn star fn, and those we can rewrite as integrals. Integrals from 0 as an integral from 0 to 2 pi of g star of x f of x. So there we've used 3,5, which is back here again, the identity operator. You can get a lot of mileage out of the identity operator. So in other words, we insert the identity operator this way and we get that. Insert it in the forms of x and we get this, and so we have then an equality of g star Gn star Fn is the same, summed over n is the same as the integral of G star F. When the F and G are the same, you just get that the length of the squared length of the ket is the integral of the square of the function. Fourier series are automatically periodic because they're sums of periodic functions, namely e to the I n x. So you can take a function that's not periodic, you create its Fourier series, then in the interval 0 to 2 pi, the Fourier series will approximate the function, but outside of that interval, the function, if it's not periodic, will differ considerably from the Fourier series, which will stay periodic from minus infinity to plus infinity. I don't know whether that cough is COVID or what. I've been trying my best to avoid COVID. Well, we'll see. Anyway, the complex conjugate of the Fourier series looks like this. And we can derive from that, taking the complex conjugate, we can draw, and then interchanging n with minus n. What we see is that the, how shall I say, the nth Fourier coefficient of the complex conjugate function is the complex conjugate of the minus nth coefficient of the ordinary Fourier series. So here, to repeat it, in other words, the nth coefficient of the Fourier series for the complex conjugate function f star is the complex conjugate of the minus nth coefficient of the ordinary function f. And so if the function f is real, we can remove the star here, and we get that fn of f is fn of f star is f star of minus n, or equivalently, f sub n is f sub minus n star, or a better way of saying it, I think, is that f sub minus n is fn star. I think that would be more reasonable. In other words, f minus n is fn star. That's a more natural way of writing this. Anyway, here you can look at these two examples, and I urge you to look at especially example 3.2. And so you just add two sine functions together, and you get beats. And that's because when you just the sum of two sine functions by a trig identity is a cosine of the difference plus a sine of the sum. And so you get this real jitter here, and then you get these beats. Okay, now the interval I took from 0 to 2 pi, but you can take any interval at all. Any interval, doesn't matter. And so you can define the Fourier coefficients like this as you integrate from r to r plus 2 pi. And one choice that is often made is to integrate from, instead of taking the interval 0 to 2 pi, you take the interval minus pi to pi. And that's fine. And you get those Fourier series. Then there's a question of where to put the 2 pi's. And what's kind of tedious is the symmetrical notation. Now, although it's tedious, I recommend it to all of you. In other words, the standard notation is this, and it's symmetrical because in the Fourier series, we have a square root of 2 pi in the denominator, and in the integral for the Fourier coefficients, we have a square root of 2 pi in the denominator. If you're a little bit shaky on Fourier series, always use this symmetrical notation. Now, people often don't, and they use an asymmetrical but more succinct notation. The problem is that you can forget where the hell the two pi's go, and even worse, you can start, or equally bad, you can start with this notation and with which you divide by 2 pi in the integral part, and then switch to the notation where you divide by 2 pi in the sum part. So you've got to keep the thing straight. And if you use the succinct notation, you have to know what you're doing and have to keep track of what you're doing. Here is a kind of nice example, and it's the function e to the minus m absolute value of x, and for positive m, and what I did here was the function e to the minus 2 times the absolute value of x. So the function looks like this. And to tell you the truth, I'm a little surprised that it goes down quite as fast, that it's so sharp here. I mean, it certainly should go down, but I'm just a little puzzled. I suppose it's that the scale here is 1 is this distance, and here that same distance is about 10. So the thing wouldn't quite look like this, but it still strikes me as being rather sharp. Anyhow, the point is that a 10-term Fourier series fits the function quite well from minus pi to pi, but of course diverges enormously outside that, because e to the minus 2 absolute value of x is by no means a periodic function, whereas its Fourier series is automatically periodic. So that's expressed here in magenta. Real Fourier series for real functions. Well, there, what you do is you write the original Fourier series 320 as d0 plus a sum over the positive integers, and then a sum over the negative integers, and then you express e to the inx, or you combine the two. You let n go to minus n here, and so you combine the two sums like that. And then you use the fact that d minus n is dn star if the function is real. And so now what we have is you expand e to the inx, you get cosine nx plus I sine nx, and here the analogous expression. And then you bring the two of them over, and you have dn plus dn star times cosine nx, and here dn minus I dn star sine nx. And these two coefficients are real. This is real, and that is real. And so what we've got in terms of the real coefficients, an and bn, we have this Fourier series. So this is the Fourier series for a real function, real in the sense of not complex. The formulas, the integral formulas for these coefficients, an and bn, are an is the integral of cosine nx, and bn is the integral of sine nx. And you notice for n equals 0, cosine of nx is just 0. So a0 is just the average value of f on the interval 0 to 2 pi times, it's twice the average value of f of x. That's what it actually is, I think. Here again here's the Fourier series for x squared, but only on this, only from -1 to 1. This is just 7 terms. For solid is 7 terms. I'm sorry, the actual function is solid. The 7 terms Fourier series is dot dash, and 20 terms is dashes. And you see the 20 terms already is almost exactly the almost exactly fits the function x squared on the just on the interval -1 to 1. These orthonormality relations can be used to derive these expressions if you want. There's something called the Gibbs Overshoot, and maybe the best way to illustrate it actually is to go back here. You see, because this function is not periodic, its Fourier series, of course, is periodic, and so the Fourier series is this dashed thing. And so the Fourier series fits the function from -pi to pi. Let me get this straight, from -pi to pi. But as you get past below -pi or above pi, it deviates. And so there's automatically some jitter there. In other words, the function doesn't, the Fourier series doesn't fit the function quite so well at the endpoints of the interval. And this is called the Gibbs Overshoot. And an example of that is if you just want the function x, so f of x is just x, so the actual function is a straight line, and the Fourier series follows it pretty well, depending on how many terms you use. Let's see what it says here. The function is the solid line x, 10 terms is dots, 100 terms is solid. And so you see the dots start to deviate before you get to -pi and before you get to pi. And the reason is that the function, the Fourier series, is periodic, so it knows it has to jump and it knows it has to dive. And so if you include more and more terms, then it becomes more faithful to the function x, but there's always this overshoot there called the big Gibbs overshoot. Gibbs's father, by the way, was a very decent man. He was a linguist at Yale, I think, and he defended the Africans who revolted on a slave ship. Anyway, stretched intervals. Instead of using an interval of length 2 pi, you can use an interval of length L, and what you do is you just rescale the exponential. By the way, there was a typo here, so the correct phase is e to the I 2 pi nx over L, and these are orthonormal on the interval 0 to L if you then divide by the square root of L. So so let me just the way you do that is you use this orthonormality relation and write the Fourier series this way, and then the coefficients look like this. And it turns out that the sum of the squares of the coefficients is equal to the integral of the absolute value squared of the function. So what you can say then is if the function is square integrable, the series formed by the absolute value squareds of its Fourier coefficients converges. So also, if you have period L, you can shift the interval. So instead, and so you can go from -L/2 to L/2. That's a common choice. And if the function is real, then you can write it this way in terms of real coefficients A and B, and cosines and sines. And these are the corresponding orthonormality relations. Now, what's very important in physics is to generalize from one dimension to n dimensions. And so instead of just having this interval, what you can do is you can keep the interval, but you can generalize it to, say, m variables, m different x's. So n dot x is n1 x1 plus n2 x2 plus up to nm xm. And then the Fourier series representation is an m-fold summation from minus infinity to plus infinity of these functions divided by the m over 2th power of L. And those coefficients Fn are m-dimensional integrals over the interval divided by the appropriate normalization factor. And so this is what's used many, many times in physics, and in particular in quantum mechanics, for example, P psi, the wave function in momentum space. And I'm going to be setting, I'm not going to get the 2 pi's, and I'm going to set h bar equal to 1. But what we would have here is d cubed x e to the I p dot x psi of x. So that would basically be how that works. And I think this would be 2 pi to the 3/2 actually. But I'm doing this live without looking, and so I'm not absolutely sure. But you, so you see this is, or equivalently, it's an integral d cubed x over 2 pi to the 3/2 e to the I p dot x x psi. So you go from position space to momentum space doing a what's called a Fourier transform. Now I've sort of leaped ahead from Fourier series to Fourier transforms here, but I hope that won't upset anyone. Differentiation and integration of Fourier series. If you integrate a Fourier series, you get something that's more convergent. And the reason is that when you integrate, you get a factor of 1 over n. So the integral of e to the I 2 pi n x over absolute value of over L gives you a 1 over n. And that 1 over n makes the series converge better. If the interval is a long interval, you get a big number out in front, but the important thing is the 1 over n, and so the series converges better. On the other hand, if you differentiate this, you pull down a factor of n, and then the convergence becomes shakier and shakier. And in particular, there's a function called the step function, or theta of x, which is 1 for x greater than 0, 0 for x less than 0, and you can say it's 1/2 for x equals 0 if you want. In any event, if you differentiate theta of x, d theta of x dx, well, this is Dirac's delta function. And you might say, well, why is that true? Well, because if you integrate, say, f of x delta of x dx from some interval, say, -1 to 1, what you get from Dirac's delta function is f of 0. On the other hand, if you write this as f of x and delta of x as d theta dx dx. By the way, I'm doing this live without notes, so I'm not certain this is going to work out. If we now integrate by parts, what we get is let's see. Is this going to work out at all? We're going to get minus, whoops. All right, hold on. I've got to get rid of these. We've got an integral minus 1 to 1 minus f prime of x theta of x dx. And so theta only works from 0. So this is for the integral 0 to 1 minus f prime of x dx. And unfortunately, I am getting minus f of 1 plus f of 0. Well, I want the f of 0, but I didn't want this f of 1. Well, I don't think I should take up any more class time here. I've screwed this up just a little bit. It's kind of obvious that it's a delta function because the derivative is 0 here, it's 0 here, it's 0 there, and it's absolutely huge at x equals 0. And I thought this would work out for me, but it didn't. Oh, wait, when we integrate by parts, we have to keep the surface terms, don't we? And so the surface terms are, that's what one needs to do. So let me say, keep surface terms and then it works out, okay? So in other words, f of 1, you need to keep the f of 1 and that's going to cancel this. All right, sorry for this a bit of a bumbled example. How Fourier series converge? Well, this section 3.8 is kind of pure mathematics, and so this is something that you should read and understand, but we're not going to make a great deal of use of it, I don't think. But I think it's good for you to hear it and to understand it, at least the basic ideas. So Fourier series obviously represents a function as a limit of a sequence of functions. So in other words, f sub capital N is this limited sum where each coefficient is given by this integral. And so that's the sense in which we're doing this. It's the Fourier series is a limit of a finite series. In other words, an infinite series is a limit of a finite series. The exponentials are periodic. The Fourier series is periodic. If the function's not periodic, its Fourier series always will be periodic, and its Fourier series defines its periodic extension, which is that if x lies in the interval that we're talking about, say 0 to L, then outside the interval, if you go outside the interval by n times the length of the interval, you still get f of x. So that's the periodic extension, which is what we saw for e to the minus 2x. The function e to the minus 2x did this. In other words, it looks like this. But the periodic extension would do this. because it has to stay periodic. A series of functions converges to a function f of x on a closed interval if for every positive epsilon at any point in the closed interval there exists an integer such that the absolute value of the difference between f of x and f sub n of x is less than epsilon when n is far enough out in the series. So that's the sense in which we mean that Fourier series converge. If it turns out that the n of epsilon and x is independent of x, then we say the sequence converges uniformly. And if the absolute value of the series converge, in other words, if the sum absolute value of Fn converges, then we say the series converges absolutely. So a function is continuous on an open interval if for every point in the interval the two limits coincide. So this is the limit of f of x minus epsilon as epsilon shrinks. So this is, here's the point, here's f of x has this particular value. And then the idea is that as you approach from below, you get f of x. And as you approach from above, you also get f of x, and you get the same number. If the limits also work on the closed interval, we just use the limit like that, and we don't worry about this or that. Then, oh, I'm sorry, I wasn't showing you that. In fact, we don't need this, do we? And I can make this bigger. Hold on, let me do. I think we're better off if we do this. Okay, so a sequence of continuous functions converges uniformly to a function f of x on a closed interval. If it does, then the absolute value of the difference is less than epsilon if you go far enough out of this out in the series, and consequently by one of the Schwarz inequalities, the difference of the of f of n integrated minus f of x integrated is less than b minus a times epsilon. And so that means that you can integrate a uniformly convergent sequence of continuous functions on a closed interval term by term. So in other words, the limit as n goes to infinity of f sub n is the same thing as the integral of the limit of f sub n, and that's f of x. So that's how we imagine Fourier series to be when we talk about them and integrate term by term. This is the mathematics that we're relying on, namely that the Fourier series converges uniformly. Now, a function that is, this is a definition, a function is piecewise continuous on a function if on an interval, if it is continuous there except for finite jumps. And I should have said, except for a finite number of finite jumps. Well, except for finite jumps at a finite number of points. So that's the same thing. At such jumps, we define the periodically extended function to be the average of the function just below the jump point and just above the jump point. So then there's Fourier's convergence theorem. So this, I'm not sure whether Fourier proved this or just stated it, but the Fourier series of a function f of x that is piecewise continuous with a piecewise continuous first derivative converges to its periodic extension. So that's the theorem. Or the result. We're not going to prove that here, but we'll take that for granted, namely that the Fourier series of a piecewise continuous function with a piecewise continuous first derivative converges to the periodic extension of the function. And it's also true that the convergence is uniform on every closed interval on which the function is continuous. And the convergence is absolute if the function has no discontinuities at all. And the examples will illustrate this. I then, what I did, to tell you the truth, is that when I did the examples in this chapter, I noticed that the convergence was greater than one would have thought. In other words, what we just get immediately is, if you have, first of all, as a definition, a function whose kth derivative is continuous is said to be in class CK. So C for continuous, and I guess for class, K for kth derivative continuous. Now, on the interval, the Fourier coefficients look like this. If it's both periodic and in CK, then one integration by parts gives you this. And the boundary terms cancel by periodicity. K integrations give 1 over n to the k. And since the derivatives of a periodic function are also periodic, so we don't get any surface terms. And so what we get is a 1 over n to the k automatically. You can then argue that so we always get this 1 over n to the k. So in other words, what I sort of expected in the examples was that the Fourier series that I was going to use as examples would all have f sub n varying as 1 over n n, wait a minute, n to the, what am I talking about? Oh, k, something that's k times derivative, differentiable. Well, 1 over n to the k, if it's k times continuously differentiable. And what I found was that, in fact, it was at a higher rate. It was 1 over n to the k plus 2. And so I wondered why, and then I came upon these arguments, namely that if fk plus 1 is piecewise continuous, as it was in the typical example, then f sub n was an integral, and it went as 1 over k to the n plus 1. And you could then argue that if f sub n was in fact bounded by something divided by n to the k plus 1. So in other words, one can expect that the kth coefficient, that for a function in class CK, or at least under these conditions, has a coefficients that go as n to the k plus 2, which is really quite remarkable. So here I took a C0 function, which means that it's continuous, but its derivatives aren't continuous. And indeed, we get 0 plus 2. In other words, it's in class C0, so it's 0 plus 2. So the idea here is that you have, in general, the absolute value of the nth Fourier coefficient for a function in class CK is goes as 1 over n to the k plus 2. So I forgot to mention CK there. So that was one example. Then in the case of C1, indeed, it goes as n1 plus 2. And then here we have Fourier series for cosine of mu x. And the idea here is that I picked an interval on which the cosine of mu x is not periodic when mu is not an integer. And so remember, it has to be not only CK, but periodic. There are then these formulas for, these are interesting formulas, by the way. The Fourier series for cosine mu x is then this, and you can then find that the cotangent, there's a cotangent series that looks like this, and cotangent of, and equivalently, you can write it this way. And so these are interesting and useful formulas. And one even gets this expression for cosine pi x as an infinite product, and for sine pi x over x as an infinite product. These are sort of special, but when infinite series, I find kind of more or less easy to understand. Infinite products, I find I find them always to be intrinsically mysterious, and in fact, infinite products are, I think one can say they're related to path integrals, which are also mysterious. So we're I think we actually out of time. Class goes from 5:30 to 6:20. So we'll pick up with Lebesgue integration next time. I'm not going to go through Lebesgue integration in great detail, but I think it's useful to think about it. It's a very nice idea when you and so we can go through it next time. Let's see. Did I forget to have chat work here? Because I don't see any. I don't see anything in the chat. Where is chat? I don't. So does somebody want to either speak up or give me a chat message for a question? Because I really ought to try to answer any question, and I haven't seen any questions. All right, I'll wait a second or two. By the way, when I put the video on YouTube, what happens is Google's computers first process it in such a way that it can be seen in low definition. Okay, thank you, Mr. Marshall. Anyway, Google's computers first produce a low definition video. And what they're doing when they are processing it is they're shortening the length. You see, these files are enormous. They're something like 200 megabytes. And then what the Google computers for example, in this region here, they realize that all those pixels inside the blue perimeter are all the same. And so they just replace them by an instruction saying that these pixels are all the same. I assume that's what they're doing. And they do that pretty quickly. But then they do the same thing to get high definition video, and that takes hours actually. So what they're really concerned about at Google is not loading up their hard drives with unnecessary huge files. I think it'd be very nice if we, I don't know, one of you may know, or some of you may know of a program that will do that, because I would like to run that program on these videos, because they're taking up a lot of space on my hard drive before because I typically leave them on my hard drive after I upload them to Google. Well, all right, I've gone on and on and on, and no one's asked a question, so I'm going to stop sharing now. Have a nice evening. I'll see you tomorrow at tomorrow is at 5 o'clock because it's a Thursday, and my plan is to finish chapter 3 tomorrow, then we can maybe slow down a little bit, because I think the students said to me that they were pretty familiar with vector calculus and Fourier series and linear algebra. But as we get beyond that to Fourier and Laplace transforms and complex variable theory, maybe some students are a little shaky with some of that, and so I'm going to slow down. But I think we've made enough time to at least fit general relativity into the course. And all right, so have a nice evening.